Welcome to the Basic Electronics series, and in this session we are learning about network theorems and DC circuit analysis. So in this session we will learning mainly Kirchhoff current law, Kirchhoff voltage law, Thevenin's theorem, Norton's theorem, superposition theorem and maximum power transfer theorem. Kirchhoff current law, it is also called as KCL. So it states that the total current entering a junction is equals to the current leaving the node or junction. So there is no charge is lost. So here you can see I1, I2, I3 are the currents entering the junction, and I4 and I5 are the currents leaving the junction. So it can also states that the sum of current entering the junction and leaving the junction is equals to 0. This can be expressed in the form of an equation, that is I1, I2, I3 sum and minus I4 minus I5, because these are the current leaving, right? So minus symbol, that is equals to 0. Next is the KVL, that means Kirchhoff voltage law. So it states that the voltage around the loop is equals to the sum of every voltage drop in the same loop for any closed network is equals to 0. Means in any closed network, the sum of all the voltage drop around the loop is equals to 0. Here VAB, having VAB is the voltage around the terminal A and B. Similarly, VBC, VCD and VDA, the sum is equals to 0. This is Kirchhoff voltage law. We can also call it as KVL. Next is the Thevenin's theorem. Thevenin's theorem means in any linear or bilateral or active network that is connected between A and B. So see here, A and B, it can be replaced by supply voltage VTH in series. That voltage having impedance ZTH. VTH means Thevenin's voltage, and it is the open terminal voltage across the terminal A and B. But ZTH means Thevenin's impedance. It can be measured across open terminals A and B by replacing all energy sources with their internal impedance. Let's prove this theorem. So consider this circuit. So here we need to apply the KVL. Now consider the first loop. So here we can write it as V minus, here current is flowing in this direction, so minus symbol, and I1 Z1 minus here current is nothing, I1 minus IL, I1 minus IL into Z3, that is equals to 0. This is equation for the first loop. Now how to simplify this equation? So to simplify this equation, we should move all the other terms to right side except V. Then it will become V equals to I1 Z1 plus, I will multiply this now only, I1 into Z3, then IL. So here we will get minus, because minus IL is there, right? That's why minus IL Z3. Now what is there here? Common term, that is I1, right? So V equals to, we need to take common I1, V equals to I1 of Z1 plus Z3 minus IL Z3. right? That is the first equation. Similarly, for the second loop, apply KVL. So here current is flowing in this direction, right? So in this direction we need to apply KVL. Now start from this point. IL minus I1, IL minus I1 of Z3 minus IL Z2 minus IL ZL, that is equals to IL ZL, that is equals to 0. But here one thing I forgot to mention, that this is also minus because current is moving in this direction. Now move all this to right side, then it will become plus, right? So now we need to simplify this equation. So multiply this to Z3. So then it will become IL Z3 minus I1 Z3 plus, right? Next is the plus IL Z2, then that is plus IL ZL, that is equals to 0. Now one thing you need to observe here, that is IL is common, right? IL here and here and here. So need to take common of IL. Then it will become minus I1 plus Z3 plus Z. This is common term. Z2 plus Z3. Sorry, Z3 plus Z2 plus ZL of IL, that is equals to 0. So this is the second equation. So now you need to take this to right side, then it will become Z3 I1 equals to Z2 plus Z3 plus ZL of IL. Now move this ZL to right side, then it will become IL, that is equals to Z2 plus, write it same, write it like this, by I1, sorry, Z3. That time we will get the value of, sorry, this is I1, right? Sorry. So I1, write it like that only, by Z3. That time we will get the value of I1. So I1 equals to Z3 plus Z2 plus ZL plus L divided by Z3. The same thing I written here. So substitute this I1 equation in this first equation. So Z1 plus Z3, here you need to write I1 equation and then keep as it is. Then equation become like this. Now you need to take LCM or multiply and divided by Z3 for this. Then it will become like this. So now you need to move this to right side, then it will become VZ3, remaining right as it is. So now here one thing you need to observe, IL is common in both sides, right? So take common IL, then this and this right as it is. Now IL equals to, if you move this to right side, this part to right side, then it will become by, it is multiplying, so then it will become divided by, right? So it will become like this. Now we got the value of IL. So now you need to multiply these terms, Z1 into Z2, Z1 Z3, Z1 ZL plus, everything should be plus, Z3 Z2, Z3 square, Z3 ZL. It should look like this. Then minus Z3, right as like that only, right as it is. Now see here, plus Z3 square and minus Z3 square is there. It will cancel each other, then you will get equation like this. Now you got the value of IL. Now you need to find Thevenin's voltage. Now we have the value of IL and I1. Now we need to find the value of Thevenin's voltage, means VTH. So in statement they already mentioned to find VTH, we need, this is open terminal voltage, and so see here we should do like this, open terminal. Now VTH means VTH is equal to VZ3 also, right? What is V? From Ohm's law we know V equals to IR or V equals to IR. Now we can write it like this, V equals to, or VZ3 or VTH equals to I into Z3. Okay, this is we know from Ohm's law. But from this figure, what you know? I equals to V by Z from Ohm's law. But here we have Z1 and Z3. We should not consider this. Why? Because this is open terminal, that is equals to 0. So now you need to substitute the value of I value you need to substitute here. So then it will become like this. Now what Thevenin's statement said, we need to find Thevenin's impedance also, right? So to find Thevenin's impedance, we need to measure Thevenin's impedance across open terminal A, B, replacing all energy sources with their internal impedance. So we need to replace this V. Why? Because we need to replace energy sources, dimension. So we need to replace this by internal impedance. Now what is ZTH? ZTH means Thevenin's impedance. So here from this equation, ZTH equals to Z1 is parallel to Z3 plus Z2. How to simplify this? Z3 divided by Z1 plus Z3 plus Z2. Now you need to take LCM. So you need to multiply and divided by Z1 plus Z3. Okay. Then you need to multiply Z1, Z2 plus Z2, Z3. Then you will get the final equation. Next, to draw the equivalent circuit, we got what? VTH, ZTH we got. So it can be constructed by connecting voltage source, that is VTH, in series with an impedance ZTH. Finally connect the load impedance which was removed from the circuit. Next we need to find a current in the equivalent circuit. We know, right, what is I? I means V by Z. From this circuit V means VTH, Z means ZTH plus ZL. So you need to substitute the values which we got from the previous equations. Then you will get like this. Now you need to add and multiply by Z1 plus Z3 to take LCM. Then it will become like this. Now these both are same, right? Z1 plus Z3 here and here. It will cancel by each other. Then it will become VZ3 plus, right, same as it is. Now you can observe equation 5 which we got here. Here. Equation 5 and equation 10 both are same, right? So IL equals to IL bar. This is the Thevenin's theorem, hence proved. Next is the Norton's theorem. So it states that any linear bilateral network that is connected between A and B, it can be replaced by current source supplying current IN in parallel with the impedance Zn. So what is IN means? It is Norton's current. It can be measured by short circuiting the terminal. How we measure it? VTH, open terminal, right? But here it should be short circuit. ZN means Norton's impedance, and it can be measured across open terminals A and B, replacing all energy sources with their internal impedance. Similar, it is like reversing type. You can get to know. Now, let's prove this theorem. Consider the same equation and apply the KVL. So, this we already discussed in the previous session. So, refer that only. How to find this? Equation 1 and equation 2 both are same. And now, from equation 2, we need to apply the I1 value. Then we will get I1 and IL value. That is also same step. Now we need to find the Norton's current. To measure Norton's current, short circuit the terminal. So to find VTH, we need to open circuit, right? But here Norton's current, we need to short circuit the terminal A and B by replacing the load impedance with a good conductor between them. So modified circuit can be written like this. Now apply the KVL for first loop, the same step which is followed in the previous theorem. For second loop it is different because here it is short circuit, right? So let's apply the KVL. So here IN minus I of Z3. One more thing you need to remember, current is moving in this direction, so it should be negative. Minus IN Z2, that is also equals to 0. Why 0? Because there is no. Why 0? Because there is no other components or impedance is present here, right? So now move this to right side, then it will become positive. Now we need to simplify this equation, then we will get the value. Then we will get this equation. Okay. Now from equation 7 we have this, right? We got I value. How means? So I equals to, move this to right side, then it will become divided by. So we got I value. Similarly we need to find the IN value also. So substitute this I value in the first equation. Then equation will become like this. Now you need to multiply and divide it by Z3 to take LCM. Remaining part write as it is. Now you need to move this to right side, then it will become multiplying. So then this part you need to write as it is. Now here you can observe IN is there in common term. So you need to take common, then this should write as it is. So and move this to right side, then you will get the IN value. So now you need to multiply this Z1 Z2 plus Z1 Z3 Z2 Z3 plus Z3 square minus Z3 square. Now Z3 plus Z3 minus Z3 cancel each other, then you will get this equation, that is I1 equation. Now we need to find Norton's impedance. In statement we already mentioned it should find across open terminal, and we need to replace all energy sources with their internal impedance, then the circuit become like this. Now Zn equals to Z1 parallel to Z3 plus Z2. So we can write it like this: Z1 Z3 divided by Z1 plus Z3. Now you need to multiply and divide it by Z1 plus Z3, then it will become like this. Now multiply this Z1 Z2 plus Z2 Z3, then we got the value of Zn. Now we need to find the Norton's equivalent circuit. So here it can be constructed by connecting current source, supplying current IN parallel with an impedance Zn, and we need to connect the load impedance which was removed from the circuit. Next we need to find the Norton's equivalent circuit is given by, so next we need to find the current, right? So to find the current, from the equation we got IL dash equals to Zn plus ZL into IN, we got from this equation. IL dash is here. Okay, we need to find this value. For that we get this, both are parallel. So these both are parallel, right? So Zn divided by Zn plus ZL into IN. So now we have the value of IN and Zn that you need to substitute here. Then now one thing you need to observe, these both are common, right? But before that you need to take LCM for this, multiply and divide it by, then it will show like this: ZL of Z1 plus Z3 divided by Z1 plus Z3. Now you need to see same written here. Z1 plus Z3 here both are same, so you can cancel it. Then you will get the equation Z1 Z2 plus Z3 Z1 plus Z3 Z2 divided by, that is only they written. So see here, this both are cancelled by each other. Then you will get this divided by this into this term. You can see here, this is the IL dash. But you need to compare this with equation 5. Both are same, right? IL and IL dash both are same, right? So see here. So hence Thevenin's theorem is proved. What it says means current flowing through the load resistor in a given circuit is equals to the current flowing through the load resistor in the equivalent circuit, Norton's equivalent circuit. Next is the superposition theorem. So in linear active bilateral network, current flowing through any component is equals to the algebraic sum of currents due to individual sources taking one at a time, replacing remaining sources with their internal impedance. So now consider the same circuit and apply the KVL for that. Then you will get the same equation which is already explained in the previous theorems. Similarly, we got the value of I1 and IL. Before that, so you need to you will get same equation when applying KVL. This equation is same. Now in statement they mentioned replace individual sources taking one at a time. So we need to take one at a time. So it can be replaced by internal impedance, right? This only written here. Now you need to apply the KVL for this. So then it will first equation is same this only, but second equation will change. How means? when we apply KVL for the second loop, I2 dash minus I1 dash into Z3 minus I2 dash Z2, that is equals to 0. Yeah, that is equals to 0. So now similarly consider V2 and replace V1. Now second equation same like this, like the first. Second equation should same, but the first equation will change because we replaced the value of V. Now you need to apply the KVL for this, then it will become minus I1 dash into Z1 minus I1, sorry, this is not dash, it is double dash. Okay, I1 double dash minus I2 double dash of Z3 equals to 0. If we move this equation to right side, then it will become positive. Now you need to multiply this I1 double dash into Z3 minus I2 double dash into Z3. Then it will look like this. Now you need to take common of I2 double dash, then the equation for this, right? Yeah, I1 double dash, you need to take common, then the equation should show like this. This is equation 5. Now you need to add equation 3 and equation 4. Then equation 3 and equation 5 and equation 4 and 6. Equation 3 is this one. You need to add with equation 5. Then the equation become like this. See here, equation 3 is Z1 plus Z3 dash, Z3 of I1 dash, Z1 plus Z3 of I1 dash. Both are same, right? So both are same. Then here Z minus Z3 I2 dash minus Z3 I2 dash equals to V1, V1 write as it is, and both here Z1 plus Z3 is there, here also Z1 plus Z3 is there. Need to take common, then you will get I1 dash plus I1 double dash, that you write here. And in equation 3 minus Z3 I2 dash, here minus Z3 I2 double dash. Z3 is common, right? So take common, minus Z3 of I2 dash plus I2 double dash, that is equals to 0. Similarly for this Z3 I1 dash, so here minus Z3 I1 dash. So you need to take common of minus Z3, then it show I1 dash plus I1 double dash. Similarly you need to take common Z2 plus Z3, then you will get I2 dash and I2 double dash. I hope you got how to add this equation. So comparing equation 1 and equation 7. So we had equation 1 this, right? Z1 plus Z3 into I1. Here Z1 plus Z3 into this I1. So we can say it as I1 equals to I1 dash plus I2 double dash. Similarly, minus Z3 of I2 dash plus I2 double dash. So here minus Z3 of I2, we can say it as I2 equals to I2 dash plus I2 double dash. It is the clear form of above equation that the current flowing through any component is the algebraic sum of currents due to the individual sources taking on a time. So hence proved. Superposition theorem. Next is the maximum power transfer theorem. It states that in any linear bilateral active network, power delivered to the load connected between two terminals is maximum when the load resistance equals to internal resistance of the source. Means power is maximum when load resistance RL is equals to RI, means internal impedance. Here you need to consider this circuit, and we know, right, I equals to V by R, but here we having RI plus RL. We have two current, two resistance. Power delivered to the load is given by, we already know, P equals to I square into R. Here load having the resistance, that is load resistance RL. Now we got the value of P. Sorry, we don't have the value of P, we have the value of I. You need to substitute the value of I, then it will become like this. Multiply V square RL divided by R1 plus RL whole square. Square is there here. Now the variation of power with the load resistance is dP by dRL. You need to take derivative. Now it will become d by dRL of this, means P value we having, right? Just mention it. Now how to apply the derivation for this? We already know U by V rule, right? V U dash minus U V dash divided by V square. V square means here we have Ri plus RL square. It will become Ri plus RL to the power 4. First you need to write V as it is. U dash means V square RL dash. Here you need to take derivative with respect to RL, right? So RL becomes 1 and V square is constant, so write as it is. Minus. Now U write as it is. You need to take the derivative of Ri plus RL square. We know, right, n square derivative is 2n, right? So it will become 2 of Ri plus RL. I hope you got how to take the derivative. Now when power is maximum means when it is equals to 0, that time power is maximum. So you need to take it as 0. Write it as 0 and this part you write as it is. So now if you move this to right side, it will become 0. Then you write as it is. Now move this to right side, then it will become 0. Then write this one as it is. RL minus 2RL means minus RL. Then Ri equals to RL. Hence maximum power transfer theorem is proved. It already mentioned in the statement, when load resistance is equals to the internal impedance of the source, the power is maximum, right? Next, for AC circuits, I will explain. Here we having AC circuits. It's like little different from the DC. So here we need to consider impedance. So Zi means internal impedance. So it is in the form of complex form. So it can be complex conjugate form. It can be write like Ri plus JXI, and ZL means RL plus JXL. So power delivered to the load is maximum when means impedance is complex conjugate of internal impedance of the source. Load impedance means ZL is complex conjugate of internal impedance means Ri of the source. Let's prove. Consider the same circuit. From this circuit we know, right, I equals to V by Z. Now we had this, right, so substitute to here, then it will become like this. Now taking modulus on both sides, then it will become I square, and here square root of V square by Ri plus RL square plus Zi plus Xi plus XL square. So we now for square root it will cancel, so we Ri plus RL square, here you need to apply the square root as it is. Multiply RL here also. Now multiply RL on both sides, then it will become I square into RL. So I square into RL, we already know P equals to I square into R, right? So you can write it as P. Then right side is same, right, as it is. Now XL is dP by dXL, and it is given by, just you need to take the derivative, okay. So dP by dXL is equals to, take the derivative. So we know, right, U by V rule. So apply the U by V rule, then it will become like this. The condition for maximum power transfer, when dP by dXL is 0, then power is maximum. So substitute 0 here, then it will become like this. Move this to right side, then you will get only this part. Now move this, even this to right side, then it will become like this. Now Xi is equals to minus XL. We got the equation. So similarly, now you take derivative with respect to XL. Now take RL, then you will get another equation. Then so maximum power delivered to the load can be obtained by substituting Xi equals to minus XL. So this is we got from this equation. I already explained, right, how to find this. So you need to apply this in here. We had Pmax formula, right? You need to apply Xi equals to minus XL. Where Xi is there, just replace it with minus XL. Then equation look like this. Now V square RL divided by Ri plus RL whole square minus XL plus XL, that will become cancel, means it will become 0. So you will get only this part, right? So similarly we get Ri equals to RL, substitute that also, then you will get 2 RL whole square, means 2 square is 4, RL square you will get. Then this one you write as it is, then you will get the Pmax value. This is the maximum power transfer theorem. Thank you.